So now we're going to continue with the second part of this first lesson with the absolute value. The formal definition of an absolute value is the distance of a number from zero. Now distance is always positive, which is probably why you learned absolute value, which is these bars right here, that it means you make it positive. And that's because you're measuring the distance from zero, and your teacher didn't really want you to measure from zero, they just wanted you to turn it positive. So whatever the number is, like 13, if you turn it positive, it stays 13. So it's not terribly complicated. Well, what's the distance from 0 to 0? Well, that's 0. It didn't turn positive or negative, it's just 0 to 0. But then I go negative 2. Negative 2 is 2 units away from 0, which means that the answer is positive 2. Now this one is when we get a little more complicated. The negative on the outside is not done at first, it's supposed to be done after you do the absolute value of 8. Well, the absolute value of 8 is 8, but it's got the negative on the outside, which means the answer for that particular problem would be negative 8. So be careful not to do the negative until after the absolute value. And then you go back to negative 4. This one, the absolute value is taking care of the negative, which means that the answer is going to be positive 4, because it's on the inside of the absolute value. Now this one's going to ask us to do a little arithmetic. First I do the absolute values, then I do the addition. So I do a little order of operations, which is PEMDAS, and I do the parentheses first. Parentheses, absolute value are on the same playing field. So I first do the absolute value of 2, and so that gives me 2, plus the absolute value is 5, which is 5, and then I do 2 plus 5, which is 7. And then finally, in this last example, you see that there's a negative on the outside, and don't distribute that. You might remember distributing, which we'll learn about later, but we don't do that here. What you want to do is do the subtraction, the 5 minus 2 first. Now, I also have a lot of students that try to turn that 2 positive first. Don't do that first. Do what's inside first, which is 5 minus 2, and so that turns into negative absolute value of 3. And then I do the absolute value of 3, which is 3. So then the answer will be negative 3. Okay? So follow the order of operations as you're doing these absolute value problems, and you'll be led to the right conclusion for each problem. Now, inequality symbols are the next thing we need to talk about. And hopefully you had a good elementary school teacher who taught you about the alligator analogy, where these inequality symbols act like an alligator looking for a hungry meal. Now, when we read them, many students get it confused as far as which one is which, whether it's greater than or less than, based on which side the X is on. So we get confused. And so I try to come up with this, that we don't read like Hebrews. Hebrews read right to left. In English, we read left to right. So first of all, this one means equals, this one means doesn't equal. Now this one, left to right, is greater. The second one is greater than or equal to. And now we've got our alligator turned the other way, which means that this is less than. And finally, the bottom one is less than or equal to. So that's how you read it. It does depend on which side the X is on as far as what you're referencing, but that's how you actually say those symbols. Okay, so let's see them in action. We're going to graph inequalities on a number line and then write the solution in interval notation. These are in set builder notation. We need to write them in interval notation. So this says X such that X is greater than 2. Well, if I was to graph that, it means that I would go to 2 and I would use maybe you learned open dot, okay? And then you're looking for X is bigger, so you get everything that's bigger than that. Now, as long as the X is on the left-hand side here, we can actually use that as like an arrow, and that's the direction we want to point. So X is greater than, that means you draw a little arrow, and that's the way you shade. Okay, so I shade bigger, greater than 2. Okay? Now, I believe the lab doesn't use the open dot version. If they do, that's fine. Otherwise, the other way is you either use a parenthesis curve or a bracket. Now, if it's open, you would use the parenthesis curve. If it was like the old solid dot, if you ever remember doing a solid dot, that's what the bracket's for. So in this particular case, I would use an open parentheses, curving towards the direction of that I shaded, and then I have that as my solution. Okay, so that's the first one. Now to write it in interval notation, I would write basically kind of what was on the graph there, which is that I started off with 2, and that was my curve, and then it goes all the way to infinity because it keeps going forever, and then of course it doesn't touch infinity, so we use another curve. Okay. Now let's do the next one. It says x is less than -3. Now again, we can use this as an arrow, which means that I'm going to shade to the left of -3. So I maybe would have used a open dot before. Now I'm using a curved parentheses, and I'm shading to the left of -3, following the arrow that this inequality symbol gives us. So the alligators are also arrows that help you shade. Now again, they're only arrows. It's only helpful if the x is on the left-hand side. So now, in interval notation, I would write -infinity up to -3 with another curve. And again, a curve means open dot. Okay. So now we've got x is less than or equal to -4. So I go to -4, and if you learn dots, this would have been a solid dot. But again, I believe the lab does the interval symbols, which means that I'm going to use a bracket. And I'm drawing it towards the left because the arrow is saying you're going to shade to the left. So I shade to the left from the bracket. Now, interval notation means that I'm going to go to -infinity. Now, I still use the parenthesis on -infinity because it won't ever touch it. And then I go up to 4, and I put my bracket. So the difference in this solution is I put my bracket whenever it's equal to. So it's less than or equal to, which means I can touch it, solid dot, it includes it, so I use the bracket. And finally, I got x is bigger than or equal to 0, so I'm at 0. It would have been a solid dot, but again, I use a bracket instead, and I'm going to be shading to the right because the arrow points to the right, and I shade it in, and my graph will look like that. My interval notation would be I can touch 0, so I use a bracket, all the way up to infinity. Can't touch infinity because you can never touch infinity, and you close the bracket with a parentheses. Okay. So now I've got some compound inequalities, and what we're looking at here is it says x such that -3 is less than x and x is less than 2. So basically x is between -3 and 2. So I could use open dots here, but again we're using intervals, so we want to use the curved parentheses, and I curve the parentheses back, and I want to shade everything between 3 and 2, which shows that x is between 3 and 2. So in interval notation you would write -3, 2, which means that x is right in the middle there, just like we have written here. Okay. And on this final example, we've got from 1 up to 5, so we will use a solid dot, in other words a bracket at 1, all the way up to a bracket at 5, and we're going to shade everything in the middle.